This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning everyone. So today is the last lecture, and what we're going to do is finish off problem set 5, which we nearly achieved yesterday, and then we'll have a look at a past exam, just so that you can get a feeling for what it's going to look like when you walk in, so that there are no surprises, just like with the mid-semester test. I showed you what it looked like, and sure enough, when you turned up, that's what it looked like. Okay, so we left off yesterday looking at this model of a feedback amplifier. Right, so what's shown here is a two-port network model of a feedback amplifier. Right, the circuit diagram would look something like this. Right, so you've got an op-amp. All right. And you've got a feedback network wrapped around from the output back to the input of the op-amp, right? And that feedback network corresponds to this path here. So it determines a relationship between the output voltage, which we want to bear some desired relationship to the input voltage, which is applied to the positive terminal relative to ground. All right, and the feedback voltage here, right? So often what's done is that you just have a resistor divider network here, all right, that effectively feeds back a fraction of the output voltage, and in that case, at low frequencies, provided the gain of the op-amp, this guy here, so the gain from whatever appears across the terminals here to the output voltage, reference to ground, is large, then the gain from the input voltage to the output voltage will be determined by 1 on F. Okay, so the smaller F is, right, the larger the gain. All right, but F, because it's coming from a resistor divider network, will always be a number between 0 and 1. Okay. So in addition to that, there's often some compensation that's put in the feedback network. All right. And this question's about saying, well, if we put extra compensation in here that looks like a lead compensator, what happens? And if we put it in such that it's a lag compensator, what happens? And of course, that's all relative to what happens when you have nothing there, just a direct connection, right? So there's no filtering at all, and you just got the resistor divider network in place. Okay, so you know, op-amps are not just constant gain at all frequency, right? The way they relate the output voltage to the voltage across the terminals of the op-amp will change across frequency. And it corresponds to having two stable poles, all right? The point of an op-amp is that it has very high gain at low frequency, all right? But it will roll off at high frequency. It's just, you know, that's the characteristics that you get when you build an op-amp, right? So inside an op-amp, there's a pair of transistors in a differential amplifier configuration, and there are resistors and capacitors in there to set bias points and so forth, and that leads to these this sort of characteristic across frequency. All right. So the closed loop system, in the style that we've been representing them as block diagrams, will look like this. all right? You can see by Kirchhoff's voltage law around this loop here that the voltage across the terminals of the op-amp is just the difference between the voltage applied at the input to the positive terminal, right, and what's fed back, right? So it's just Kirchhoff's voltage law around there gives us this element of our block diagram, okay? The transfer function of the op-amp relates VM and Vout, right? And then VF is related to Vout by the characteristics of the feedback network, right? So that's F, the resistor divider, plus whatever compensator we put in there, right? So it's a standard closed loop system, all right? We want the transfer function from V in to V out to be some desired thing, particularly at low frequencies, and the transfer function from here to here is just given by this, right? So the open loop transfer function is the product of this and this, right? It's what you get when you break the loop here and follow around the loop, just like in every other case that we've seen, right? So just because we're looking at wanting this to be something doesn't change the fact that the open loop transfer function is still the product of these two bits, all right? So, we left off looking at, the Bode plots for each part, all right? Now, the overall open loop transfer function, which is the product of all these things, all right, can be found by, on the magnitude plot, adding the corresponding bits together. That's what you get when you're working on a log scale, right? The magnitude of the product will be the sum of the magnitudes on the log scale magnitude plot. And similarly, the phase will just be the sum of all the phase components, all right? And the thing to note in the solutions here is that just so that everything can be drawn on the same diagram, the lead compensator, which always gives you positive phase, all right, is drawn down here by multiplying it with -1. Right, just so that it can fit on the same thing. But this is really up here, all right? So you can see that this is a lag compensator because the pole brings you down before the zero flattens you off. This is the lead compensator because the zero kicks you up before the pole flattens you off again, right? So that's how you can identify whether it's lead or lag, right? Lead, the zero kicks you up first, the pole then flattens you off, right? And you always get positive phase, right? Because the zero gives you positive phase and then the pole pulls it back down again, all right? Whereas the lag compensator, the pole starts rolling you off and then the zero flattens you out. And of course, the pole is always giving you negative phase and then the zero flattening you off here brings you back up, right? So that's how you identify lead and lag compensators from a Bode plot, all right? In addition to that, we have F, okay, which is the resistor divider network. It's always a number between 0 and 1. So when F is 1, it's just this line here, right? Which means on the log scale, you're just adding 0 to whatever the loop shape is. But if F is, say, 0.1, then it'll be down here and it'll bring everything down, okay? So in the reference solutions to these questions, which are really about saying, for what value of the resistor feedback network ratio do we get a phase margin more than 90? So in the case where there's no compensator, right, just the resistor divider network, rather than figuring out how different values of F pull the magnitude plot of the op-amp transfer function down, because we're multiplying by a number that's less than 1, you can think in terms of how varying F just changes where the 0 dB line is, right? Moving the 0 dB line up is the same as moving the other plot down, right? So this is the case where the open loop transfer function is just F times A of S, where F is some number between 0 and 1, all right, we've got C of S equals to 1. So that's why they've been greyed out here, because they're not playing any role in this case. All right, so when F is equal to 1, all right, then we get a crossover frequency here, right, at this frequency. It's where the open loop transfer function has a gain of 1, right? This is what the phase looks like, all right? You can see that there are the two poles in the op-amp transfer function, right? One pole at a lower frequency that creates minus 90 degrees of phase shift, right? And then another pole at higher frequency again that gives you another minus 90 degrees phase shift, right, over a higher range of frequencies now. All right, so this is just what the phase plot of A looks like. Multiplying by F, which is a positive number, is not going to change the phase plot, right? Because the phase of F is just 0. Okay, so when F is 1, this is the crossover frequency. How much phase margin do we get? Well, we get about 45 degrees, okay, when F is 1. So that's, that's a reasonable phase margin, but you'll probably still get some oscillations in the closed loop response, but they'll be fairly well damped. 45 degrees is pretty good. All right. If we now change F so that the 0 dB line moves up to here, which is the same as, bringing this down by a corresponding amount, you end up with a new crossover frequency. So changing F changes the crossover frequency. And if we set F such that the crossover frequency is here, then we get 90 degrees of phase margin. If you've got 90 degrees of phase margin, you won't get any oscillations in your transient response. All right? And of course, if you choose F to be any value smaller than the one that moves the 0 dB line up to here, then you will just get more phase margin. Okay? So that's how you can use a Bodie plot to figure out, what the phase margin is and how to choose a parameter to get the phase margin that you want. Okay. If we now look at putting in in this case, lag compensator, right? So now we're looking at lambda being F times C of S, but the lag one, which is denoted by C minus times A of S, right? Then here's A, right? There's one pole kicking you down, there's the other pole kicking you down, so that here you're going down at minus 40 dB per decade, right? Here's the lag compensator, right? That's been fixed in the question, right? So there's nothing to choose here, but you can choose F, all right? So if we just look at what happens to the magnitude plot when we multiply these two things together, this is what A is, right? And I have to add to that on this log scale what C is doing, right? And C is always negative, so it pulls it down, right? It pulls it down, by less here, right, than it does here, okay? But beyond this point, it's pulling it down by the same amount, all right? So this dotted line here is showing you what the product of these two is, right? So what happens to the phase plot? Well, this is what the phase of A looks like. That's consistent with two stable poles. In total, they give you minus 180 degrees phase shift, all right? This is the phase of the lag compensator, all right? So you sum the two, right? Because, the phase of C minus and A is equal to the phase of C minus plus the phase of A, right? Phases just add, and you can see that you end up with this as the result, the dotted line here, right? So it's just coming from adding these two things together, all right? We're adding negative numbers together, so it becomes more negative. Changing F, we can think of as just changing where the 0 dB line is. Multiplying by a number less than 1 will pull this dotted line down, but that's the same as saying, well, it's like moving the 0 dB line up, all right? And we're looking for where the phase margin will be 90, right? So here's our phase plot. Multiplying by f doesn't change that, right, because the phase of f is 0. This is where it's 90 degrees, right? So we want this to line up with the crossover frequency, and we can make this the crossover frequency by choosing f to move the 0 dB line from here to here, all right? And if we choose, so that will correspond to multiplying by a number less than 1 to move it up, okay? And if we multiply by a smaller number again, that would shift the crossover frequency further to the left and give you a higher phase margin in this particular case, right? Whereas if we if we left f with 1 as 1, the crossover frequency would be here, right? And you would get a slightly smaller phase margin, all right? But the point here is that with a phase lag compensator, the lag compensator always pushes the phase of the, if you like, open loop plant transfer function closer to minus 180, right, or further down, right? Whereas a lead compensator does the opposite thing, all right? So here's A, right, the solid line there. This is what the lead compensator does, all right? So it pulls it down, the magnitude plot down by more at low frequencies than it does at high frequencies, right? Which is why you end up with this as the open loop transfer function gain across frequency, right? So this dotted line here is just the sum of this line and this line here, because we're working on a log scale, all right? The phase of the lead compensator, we've just drawn it down here, but really it's up here, right? This is the phase of minus 1 times the lead compensator, right, which shifts it down by minus 180 degrees, which is the phase of minus 1, right? But really it's up there. So what we're doing is adding to the phase of A, this solid line, something that does this, right? So it's bringing it up, it's pushing it away from minus 180 degrees. That's what a lead compensator does, all right? And so if we're looking for a phase margin of 90 degrees, find where the phase of the open loop transfer function is 90 degrees. It's at this frequency here, right? How can we make the crossover frequency line up with this 90 degrees of phase margin? Well, in this case, it corresponds to choosing f to be equal to 1, right? Here's the crossover frequency for the magnitude, for the open loop transfer function. Okay, it's where it crosses the 0 dB line, where the magnitude plot crosses the 0 dB line. All right, so the point here is that the lead compensator has helped us achieve a wider bandwidth than would be achievable with a lag compensator, right? For the closed loop. All right. All right, so these are just examples showing you how to read things off Bode plots. All right. There are exam questions like this. All right. So it's worth getting your head around it all. Are there any questions before we have a look at the exam? Yeah.
In this graph, we have at 0 dB approximately equal to 90 degrees. Can't we consider plus or minus 5 degrees as error and say that both lead and lag would be given the same output of 90 degrees?
Sorry, I couldn't hear that last bit.
In the lag as well, when
Yep.
f is equals to 1, it is at 0 dB approximately equal to 90 degrees.
Well, it's close.
So can't we say that plus or minus 5 degrees could be considered as error and say that both lead and lag are doing the same thing? For example?
But the crossover frequencies are very different. Even if I put the crossover frequency here and still got 85 degrees of phase margin, which will give you over-damped closed-loop poles, right? So no oscillations. As soon as you've got more than about 75 degrees of phase margin, assuming that your closed loop is dominated by just 2 poles, those poles will be over-damped, right? So no oscillations. So sure, we could leave f equals 1, right, and get the phase margin close to 90, 85, still no oscillations, but the crossover frequency will be 100, whereas with the lead compensator, the crossover frequency is, 100, 200, 300, 400, 500, 600, 700, right? So the difference between the two closed loops is that this one will have so we're interested in this transfer function, right? That's what tells us about the relationship between V in and V out, okay? That will have a bandwidth, right? And the bandwidth will be consistent with the crossover frequency, right? So your ability to get signals through the system without much distortion, right, is better with the lead compensator because it has a wider bandwidth, right? Because of the higher crossover frequency, right? Whereas with the lag compensator, right, you end up with the bandwidth down here, like maybe it's like nearly an order of magnitude lower, right? So you're not going to be able to put as high frequency input signals in without getting distortion at the output, right? So you wouldn't really use a lag compensator here, right? It's not helping you achieve anything useful, right? And relative to what happens when you have no compensation at all to get the 90 degrees phase margin, the lag compensator is not moving it much relative to what you can get without any additional compensation at all. So why would you put it in there? So the point is that the lead compensator is allowing you to get a wider bandwidth amplifier. Yeah? Any other questions? Yeah, and when you're building electronic circuits, right, if you can avoid putting components in, you would avoid putting components in, right? So, the lag compensator is not doing anything much relative to just having the resistor divider network in there. So why would you put it in there? But for the lead compensator, and really all you're having to put in to that little box that I drew is one more resistor and one more capacitor, right? And you can see that it widens the bandwidth significantly, right? But the gain that we're getting overall at low frequencies will just now be close to 1. So the amplifier will be acting just like a buffer, right, rather than pumping up the gain. To pump up the gain, you need F to be less than 1. So if you wanted the gain of 10 from VI to VO, you'd have to choose F to be 0.1, right? And so in that case, that would put the crossover frequency down here again anyway, right? Anyway, there's lots of other things to consider when building an amplifier circuit as well. This is just an example with some context to show you how to read phase margins and so forth off a Bode plot. Make sense? Any other questions? Yep.
Just to confirm, if we mention the bandwidth as a term, are we actually talking about the open loop transfer function?
Well, when we're talking about the open loop transfer function, we've always used the term crossover frequency, right? But the crossover frequency, so if we look at your standard closed loop, lambda sitting in there, and you're feeding that back, right? And we know the transfer function from here to here will be lambda on 1 plus lambda, right? So that's T. Okay, and if you look at what T is when lambda has a classical loop shape like that, right, where that's the crossover frequency, right, then T will look something like, like this, right? And how much it peaks up depends on what the phase margin is, right, which relates to the phase of the open loop transfer function at this frequency. But you can see that the crossover frequency for lambda is related to the bandwidth of T. Right, if I make the crossover frequency over here, right, I get a wider bandwidth T. So they're not exactly the same number, but they're closely related, right? So the crossover frequency for the open loop transfer function is very closely related to the bandwidth of the complementary sensitivity function. Where bandwidth is just meaning the range of frequencies over which the gain is 1 before it starts rolling off.
Yeah.
Yep. So yeah, I'm not trying to say the 3 dB point, blah blah blah. You know, that's kind of too much detail for the message I'm trying to get across, and it doesn't really matter, right? We're trying to understand what happens when we move one thing in terms of the effect on another, right? So moving the crossover frequency to the right, okay, will extend the range of frequencies over which the complementary sensitivity function is 1, assuming we have sufficient gain in the open loop transfer functions at frequencies below that. Make sense? And you can understand that in terms of the sensitivity function that tells you how the error depends on the reference, right? That function looks like this, right? And you could talk about the bandwidth of this being the range of frequencies over which it attenuates, right? As opposed to thinking about the range of frequencies over which a function has gain 1 or close to 1. But these are just labels, right? So, you know, I don't want to give too much meaning to bandwidth and say it is the 3 dB point, blah, blah, blah. Yeah, that's not. That's more important when you're talking about filter design, right? So, yeah, we're just relying on the fact that there is this loose relationship between the crossover frequency and the bandwidth of the complementary sensitivity function. Of course, if the complementary sensitivity function ends up peaking like that because you've got not a very good phase margin, then really the range of signals that get through without attenuation is only up to here, without distortion is only up to here, right? So you probably wouldn't call that the bandwidth. You would call that the bandwidth. But if you've got better damping, right, then those numbers are close together. But nonetheless, moving the crossover, all of this stuff happens, right, where it starts to not be 1 anymore, right, happens around the crossover frequency for the open loop transfer function. Make sense? Any other questions? Yeah, and as soon as you get peaking, lots of peaking in the complementary sensitivity function, and you'll get the same amount of peaking in the sensitivity output sensitivity function. Moving things to the right will not make stuff faster, right? Necessarily. Moving things to the right only leads to faster responses in terms of settling time, as long as you don't get much peaking. Right, and it's the same as thinking on root locus plots, and if we have a system like this, increase the gain, these come together, this guy's getting faster, but when it splits apart, right, it stops getting faster, and it just you get more oscillations, right? And if you look at what would be happening to the complementary sensitivity function, for the low gains that put you here and here, you're getting complementary sensitivity functions that will just roll off without much peaking, right? And as we increase the gain further to move the poles like that, it's going to move it across like that, right? So you're extending the bandwidth and making it faster. But as soon as you put the gain so that they're here, it starts peaking up again, right? And it'll move to the right, but while it's peaking up, and so you're not getting faster response from the perspective of settling time anymore, and you're just getting more oscillations because you're getting less damping. Right, so you can only think of a relationship between pushing the crossover frequency to the right and reduction of the settling time until you get peaking in the response. Right, but we've also seen examples where pushing the crossover frequency to the right reduced the amount of peaking that we had. Right, so there's not just a generic rule that you can apply saying if you push the crossover frequency to the right, you'll get more peaking because you'll reduce the phase margin. Well, it depends on the situation. Sometimes it does, sometimes it doesn't. And we've seen examples, and if you go and look at problem set 4, in problem set 4, there are 2 cases considered in one case, pushing the crossover frequency to the right led to an improvement of the phase margin, reduced the peaking, right? And in the other case, pushing it to the right, reduced the phase margin and increased the peaking. So there's no generic rule that you can come up with. You just got to look at the situation you have and understand what the phase margin means and how that relates to, you know, how much peaking you get in the sensitivity functions. All right, so just understand what things mean, understand how to do the analysis, and apply that to the specific situation you're dealing with. There are no generic rules that apply everywhere. The only thing that always applies is what the phase margin means. It's the phase of the open loop transfer function at the crossover frequency. The crossover frequency is where the open loop transfer function has a gain of 1, right? And there will always be, and what remains the same is that there's a relationship between how much peaking you get, right, and the phase margin, right? Because the phase margin, if we look on a Nyquist plot, is telling you, you know, how close you are to the critical point -1, right? And it's telling you that in terms of the angle of the open loop transfer function at the crossover frequency, right? That's why I've drawn a circle of radius 1 here. Okay, so that's the little vector that tells you what the open loop transfer function is at the crossover frequency, where it has a gain of 1, right? There's your phase margin, and we've seen lots of times that this little vector here is 1 plus lambda. Well, you know, so the size of this thing here is the magnitude of 1 plus lambda at the crossover frequency, right? And the output sensitivity function at the crossover frequency has magnitude 1 on 1 plus lambda j omega c. All right, so if the phase margin is small, this will be small and the sensitivity function will peak up, right? So whether moving the crossover frequency to different points causes this depends on whether or not moving the crossover frequency to different points changes the phase margin in a way that makes it bigger or the way that makes it smaller. Both can happen, right? But if you understand the meaning of all these things, you'll be able to interpret what happens, and that's the important thing. Make sense? All right, let's have a look at a past exam. So this is the exam from 2017. All right, the structure of the exam this year is exactly the same. All right, the first page will look like this. All right. So the exam is open book. That means you can bring in anything you like. All right, any printed or written material you like. The only electronic equipment you will be allowed to use in the exam is one of these two calculators. Now, I don't think you would really need a calculator, but if it makes you comfortable having a calculator there, bring it in. All right? You know, it's not that you won't be able to use a calculator, it's not critical. Okay? But if you're going to bring one in, just bring one of these two. Right, these two are the only ones that the invigilators are prepared to check, right? So, yeah, no other electronic equipment. We don't have the Melbourne School of Engineering stickers anymore, so that doesn't apply this year. Like the 2017 exam, there will be 4 questions, all right, for a total of 50 marks, right? Questions are of unequal value, right? So it's not like, there's 12.5 marks per question. It's not the way the marks are distributed, right? There's more marks associated with questions 3 and 4. Okay. As we'll see, you provide your answers on the exam paper, right? So there are boxes like the examples that you've seen on LMS where you are required to put your answers. That's the part of the exam that will be marked, right? So I would encourage you to use the blank side of each page, right? So there'll be a printed side on each page, and then the other side will be blank. You can do rough working there, right? So figure out what you're doing first before putting the answer in the box. All right? In principle, I'm not going to look at the blank page where you do rough working, but sometimes I do, right? But in principle, I'm going to look inside the box, and I'm only going to look at the blank side of the page if something's gone horribly wrong inside the box. Okay? So, you know, just don't rush. There is extra space at the end of the exam, and if you use it, make sure you point to it from the box where the answer is required to go, so that I know to go and look at it. All right? All right. So you can also ask for a script book, right? If you prefer to do rough working in the script book, but I won't grade what's in the script book. It'll be collected at the end of the exam, but I won't look at it. All right? So, but if you need a script book, you'll have to ask for one. There won't be one on the table already. So the exam. So here's an example of, you know, there's a blank page, right? So the back side of every page is blank like this, with a little, you know, statement up the top saying this is intentionally blank. So you can do your rough working there if required. So, you know, the first question is always about linearization, right? So as I've mentioned lots of times, this is not a course on, you know, this is not a course about physics and stuff. So it's not about deriving models. It's about doing things with models. And so, you know, I give you models, and in this case, you know, it's a nonlinear model because there's this constant term added on, but there's also this nonlinearity here, and this is the description of the nonlinearity, right? But it's an ordinary differential equation model that is nonlinear, right? And you have to linearize it and say something about the linear approximation, right? So you work in the time domain to do the linearization in the way that we've seen many times, okay? And then you might have to take the incremental model into the frequency domain to say something about, you know, where the poles and zeros are. Is it stable? Is it not stable? You know, what might the step response look like? That sort of thing. All right. So it's really about doing something, fairly standard stuff, you know, with models that are given to you. Right. So it's not about deriving the models, and these pictures are just there to provide context for those that, you know, find it useful. If this is confusing for you, just don't look at it. All right. And just work with the model that's given. Okay, so question 1 this year is another question on linearization, kind of like this. It's a different physical system. All right, but the equations will be given to you, and you just work with them, right, to find an incremental model. All right, about which you'll be asked some questions. Okay. So don't freak out as well when you see that, you know, the exam's got 41 pages. The reason it's got 41 pages is because the blank pages have to be numbered, right? And because most of the exam paper is space for you to put your answer in, right? If I took all the answer boxes out, the exam fits on 5 pages, 5 or 6 pages, right? So it's not, you shouldn't worry about that. Okay. Question 2 this year will look pretty much exactly the same as question 2 on this paper and question 2 on the, you know, 2015 paper, right? These are these little short answer type problems, right? The first part is always about saying, well, here's some pole zero plots for some transfer functions. Here's some step responses. Match the pole zero plots to the step responses. All right? So, you know, that question's always there, and this year is no different, right? What changes year to year is, you know, the locations of the poles and the zeros. Okay? So that should be fairly straightforward, right? So you're looking for, you know, whether there's undershoot or overshoot and whether there are oscillations, right? We know that, you know, you only get oscillations when there's a non-zero imaginary part for the poles, right? When you have a right half plane 0, you might get some undershoot, right? And undershoot's about moving in the opposite direction to where you'll end up, right? And from a pole 0 plot, you can't tell the sign of the DC gain, right? And so the step response, to a positive step in, the response might be to a negative value, final value, right? If the DC gain is -1. And in that case, if the DC gain is -1, the step response to a positive step, if there's a right half plane 0, will go in the wrong direction first before reaching a steady value, which is negative, right? If the DC gain is 1. So, undershoot is not about going down and then up. It's about going in the direction that is opposite to where you will end up, right? And if the DC gain is negative, then you will end up at a negative final value for a positive step in, right? So, bear that in mind. You can't tell what the DC gain is by looking at the pole 0 plot. Okay. So, look for things like that. When you have slow zeros that are closer to the imaginary axis than the dominant poles, then you get overshoot, all those sorts of things that we've seen before. The second and third parts of question 2 are really about, just some simple calculations of the kind that we've been looking at, recently, including the last problem set. So this is about phase margin, really, or this one's about gain margin, right? And remember, gain margin is about the frequency where the open loop transfer function has a phase of -pi radians, right? And the gain margin is 1 over the gain at that of the open loop transfer function at that frequency. Right? It's how much you'd have to scale the gain by to move the crossover frequency to where the phase is -pi, which will give you 2 closed loop poles on the imaginary axis. To make the Nyquist plot hit the -1 point. All right. So, here you're given functions with certain parameters, right? And so again, use the specifications to write down some equations that constrain the parameters in the way that we've been doing for the last, 2 weeks, right? To figure out what the parameters need to be or how they have to be related to each other. All right, so here, it's not that you get a numerical answer, you get a relationship, right? But those relationships can be written down by just using the definition of what the gain margin is. And I just told you what it is, right? And this one's a root locus type question, right? So this year has exactly the same structure. Question 2 has 3 parts. The first part is about matching pole 0 plots to step responses. I can't remember what the second part is, but it's probably got to do with phase margin or something like that, or gain margin. And there's this root locus type question. All right. Questions 3 and 4 are more about control system design and analysis. Okay. So in 2017, the context was, this launch vehicle, right, for a satellite, so just a rocket. Okay. Again, you're given the dynamics. You don't have to derive them. You're given the model, right? In fact, this is an incremental model. It's already linearized, right? You should be able to see here, because the coefficients change sign here, that this is going to be unstable, which is not so surprising. It's like your inverted pendulum example, right? You're given lots of details about what everything means in the model, and so really the question's about doing things with the model. It's not about deriving it. Okay. It describes a control system. In this case, it's about maintaining a particular attitude, and the control system is described verbally here. And the first thing is about draw a block diagram, right? Well, we've done that lots and lots of times. Okay, and then the next questions are about saying, well, what happens when we use proportional gain control? right? Can you stabilise the system with proportional gain control? What kind of closed loop responses do you get as you vary the proportional controller gain? What can you do if you use a more sophisticated, compensator? This is just a PID compensator, right? And you're asked to choose the parameters of the compensator in order to achieve phase margin and crossover frequency specifications. Well, we just did that in problem set 5, and we did it in problem set 4. Okay, qualitatively describe the behaviour of the system in terms of its steady state response. What happens if we perturb the open loop transfer function in some way, to account for the fact that a sensor has a low pass filter on it or something like that, analyse what happens in terms of a Nyquist plot. And again, I'm not going to ask you to draw the Nyquist plot. I'm going to give you the Nyquist plot and maybe ask you to add to it and interpret what the Nyquist plot reveals. Okay? So the only thing I do with these sorts of Nyquist plots is I take the arrows off. All right? So I don't tell you which is the direction of increasing frequency. Okay, so you've got to work it out, but you work it out on the basis of looking at the open loop transfer function, which I give you, right? And thinking about, what the phase is at low frequency, what the phase is at high frequency, what the gain should be on the basis of where the poles and zeros are, right? To figure out, as we've done, many times, well, a few times at least, to figure out what's the direction of increasing frequency, right? In this particular example, it's hard to see all of the detail of the Nyquist plot in one shot, right? Because it's got this little bit in here that you can't quite see, and so in situations like that, I give you the zoom in plot as well, right? So these are not two different Nyquist plots. This is just a zoomed in version of what's happening there, right? Because there's another flips around in there, okay, and changing the gain could move the critical point from where it is to inside there, which will change the number of encirclements that you get, and that has an impact on stability, right? So this year there's a very similar question, right? And you'll be given, a big chunk of a Nyquist plot, and you'll be asked to figure out, what's the direction of increasing frequency. In situations like this where you have open loop poles at the origin, which you will, because the controller in this case has a pole at the origin. So we know that when we have poles at the origin, we've got to go around a little indentation as we're moving around the D contour, and you get minus pi radians change in phase for every pole that you go around with the little indentation, right? So, of course, those things aren't drawn on these plots, right? So to figure out in the end how many encirclements of the critical point you're getting, you're going to have to effectively draw those in, right? So you'll have to do a similar thing this year. Okay, so practice these sorts of questions. The last question is again about design of a compensator, but you don't just get to arbitrarily choose the compensator type. There are 4 types of compensators that are given, right? If the context confuses you, don't look at it, right? I've still given you the closed loop, right? The open loop transfer function is the product of this and this and this, right? Just like in the example we saw today. So you don't have to work out what this is from this. I give it to you, right? Then ask you to analyse this for different controllers. Again, I don't ask you to draw the Bode plots. I give you the Bode plots. But I want you to match the different Bode plots to the different compensators that you get. Right? So I'm giving most of it to you, right? I'm really just testing. Do you understand what these things mean, right? So you don't have to worry about drawing Bode plots. I give you all of them, and then you've just got to match them to the different compensators you get. Okay? Same sort of thing this year. All right? And then you get to read stuff off the Bode plots, like, you know, what's the phase margin? What's the crossover frequency? All those sorts of things, right? And then you get to ask to interpret the step responses, right? Or the impulse responses that you might get. And so instead of getting you to draw them, right, I give them to you for the different controllers, and you just got to match the responses to the controllers. How do you do that? Well, on the basis of, you know, the stuff you identify from the Bode plots of the open loop transfer functions for the different controllers, right? So you look at these, you know, say, well, that one, you know, this is more oscillatory than these responses are slower than these responses, you know. How does that translate into, you know, phase margin characteristics of the open loop transfer function, crossover frequency characteristics of the open loop transfer function for the different types of compensators, right? But, you know, I've given you the Bode plots. You should just be able to read them off. Okay? So, you know, there's a similar setup in the exam this year. Yeah. What changes is the physical system context, right? But the structure of the question is exactly the same. All right, so a lot is given to you in the exam, right? And if you know what things mean and you understand how to interpret them, you'll be fine. Right? So you don't have to stress about, you know, oh, how am I going to draw a Bode plot and get the crossover frequency exactly right and all that. It's given to you. Okay? All right, are there any questions? All right, so there should be no surprises when you walk into the exam. It'll look exactly like this. The context changes. That's all. All right. Well, if there are no questions, then that's it. Good luck in your exam.
The past paper you just saw before is the 2017, right?
Yeah.
You didn't post the...
No. I've seen it now.
So will you do it now? I mean, will you post it on the LMS, or we can just...
Well, you can just look at it on the
Okay. So I found that the past paper I found in the Federal Library website is kind of different.
Yeah, much older exam.
But I found some...
Oh no, that might be the semester 2 exam.
Yes.
Yeah. Well, don't look at those. I don't teach the semester 2 version. Someone else does it.
So we don't need to look at the...
No. Look at the ones I've given you.
Just one. So what do you find at the end of if they, so these again, like typical, so
It'll go up first.
Yeah. What if the steady state? What if the steady state value will be 0?
Yeah, there's more work to do to figure out what happens. Right? So if the steady state is 0, that means you've got a pole at the origin as well, right? No, you've got a 0 at the origin. Right? So okay. Remember the amount of undershoot that you get.
Yeah.
Right. How are you going to get a response, a steady state response to a step input, right? Your transfer function is going to have an S on the top to cancel it out, so that when you do the limit as S goes to 0, there's S times the object, right? You'll get 0. So you need a 0.
Yeah.
So how much undershoot you get is determined by the 0 that is closest to the imaginary axis, right? And when it's on there, you don't necessarily get any undershoot, right, in the usual sense. And it doesn't even make sense, because undershoot is about saying, well, it moves in the direction opposite to where it ends up. But if it's going to end up at 0, you know, what's opposite? That or that, right? You can't tell. But it's not like you have a right half plane 0. You have a 0 on the imaginary axis at s equals 0. So it's not an undershoot situation. You shouldn't think in terms of undershoot if you've got a 0 on the origin.
But there will be, it can go up and go.
It could go down. Depends on the sign of the system at high frequency.
But it does not mean it is undershoot or.
Yeah. But you're not being asked to say to